Quantum computing stands at the forefront of technological innovation. It represents a leap beyond classical computing paradigms. At its core, quantum computing harnesses the peculiarities of quantum mechanics. This field is set to revolutionize how we process information. Unlike classical computers which use bits, quantum computers use qubits. Qubits can exist in multiple states simultaneously, thanks to quantum principles. The theoretical foundation of quantum computing lies in quantum mechanics. Quantum mechanics governs the behavior of particles at atomic and subatomic levels. It introduces concepts such as superposition, entanglement, and tunneling. These principles enable quantum computers to solve complex problems more efficiently. While still in its infancy, quantum computing promises transformative impacts. The development of quantum computing began with theoretical physics. Pioneering scientists like Richard Feynman and David Deutsch envisioned its potential. Their work laid the groundwork for modern quantum computers. Today, researchers and companies worldwide are racing to build scalable quantum systems. With continued advancements, quantum computing could redefine multiple industries. To truly grasp how quantum computing achieves its extraordinary capabilities, we need to delve into the fundamental principles of quantum mechanics, the strange and counterintuitive rules that govern the behavior of particles at the atomic and subatomic level. Chapter 2: Heisenberg's Uncertainty Principle. Heisenberg's uncertainty principle is a critical component of quantum mechanics. It posits that certain pairs of physical properties cannot be known simultaneously with precision. For example, one cannot precisely measure both the position and momentum of a particle. This principle challenges the deterministic nature of classical physics. In quantum computing, it affects how we measure and manage qubits. The uncertainty principle highlights the probabilistic nature of quantum systems. This uncertainty is intrinsic to the system. For quantum computing, it means calculations are based on probabilities. This approach can lead to faster and more efficient problem solving. However, it also introduces challenges in error correction and qubit stability. Understanding this principle is crucial for advancing quantum technologies. It impacts how qubits interact and how information is processed. The inherent uncertainty requires new methods of computation and data handling. As a result, researchers continuously work on refining measurement techniques. These advancements are necessary for developing reliable quantum computers. Despite its challenges, the uncertainty principle offers opportunities. It allows for unique ways of processing information. Quantum computing exploits this to perform tasks beyond classical capabilities. As we better understand quantum mechanics, we can harness its power more effectively. Chapter 3: Superposition and Qubits. Superposition is a fundamental principle in quantum mechanics. It allows particles to exist in multiple states at once. In quantum computing, this principle is embodied by qubits. Unlike classical bits, which are binary, qubits can be both 0 and 1 simultaneously. This capability exponentially increases computational power. Qubits are the building blocks of quantum computers. They enable parallel processing by existing in superposition. This allows quantum computers to perform many calculations at once. Classical computers, in contrast, must process each bit sequentially. The result is a dramatic increase in processing speed and capacity. Superposition is not without its challenges. Maintaining qubits in superposition requires precise conditions. Any disturbance can cause qubits to collapse into a single state. This phenomenon, known as decoherence, is a significant hurdle. Researchers are developing techniques to preserve qubit stability over time. The potential of superposition extends beyond computing speed. It opens new avenues for solving complex mathematical problems. Quantum algorithms like Shor's and Grover's leverage superposition to outperform classical algorithms. As we refine our control over qubits, we unlock new possibilities in computation. Entanglement is another cornerstone of quantum mechanics. It describes a unique correlation between particles. When particles are entangled, the state of one affects the other, regardless of distance. This property is crucial for quantum computing and communication.
Entangled qubits can transmit information instantaneously. This phenomenon challenges classical notions of information transfer. In quantum computing, entanglement allows for more intricate data processing. Multiple qubits can be entangled to perform complex operations efficiently. Creating and maintaining entangled states is intricate. External interference can break entanglement, leading to errors. Quantum error correction methods are essential to preserve entangled states. These techniques ensure accurate computation by minimizing disruption. Entanglement also plays a pivotal role in quantum cryptography. It enables secure communication through quantum key distribution. This method uses entangled particles to create unbreakable encryption. As quantum technologies mature, entanglement will become more integral to data security. Quantum entanglement represents a paradigm shift in information theory. It offers possibilities that classical physics cannot achieve. By mastering entanglement, we can develop advanced computing and secure communication systems. The ongoing research strives to harness this potential fully.
Section 5: Quantum tunneling and its implications. Quantum tunneling is a phenomenon where particles pass through barriers. Quantum mechanics allows particles to tunnel through energy barriers. This principle has significant implications for quantum computing. It allows particles to explore multiple paths simultaneously. Tunneling enhances processes like quantum annealing. It impacts the design of quantum circuits. Beyond computing, tunneling influences electronic components. It enables new devices like tunnel diodes. Quantum tunneling extends the reach of quantum mechanics into practical technologies. Section 6: Quantum versus classical computing. Quantum computing surpasses classical computing due to its unique principles. The key advantage lies in its ability to process information in parallel.
This is made possible by superposition and entanglement, enabling massive computational power. Classical computers use binary bits for computation. They perform calculations sequentially, which limits speed.
Quantum computers with qubits process multiple possibilities simultaneously. This parallelism allows for solving problems that are infeasible for classical systems. Interconnectedness is another strength of quantum computing.
Entangled qubits share information instantaneously. This leads to more efficient algorithms and data processing. Quantum systems can tackle large datasets and complex simulations effectively. Despite its advantages, quantum computing is not always superior. It excels in specific domains like factorization and search algorithms. Classical computers remain practical for everyday tasks and general computing needs.
The integration of both systems could yield versatile computing solutions. Quantum computing's true potential lies in addressing complex challenges. It offers new approaches to optimization, simulation, and data analysis. As quantum technologies advance, their applications will expand. The synergy of quantum and classical systems will shape the future of computation.
Section 7: Real-world applications. Quantum computing holds promise for various real-world applications. It can revolutionize industries like pharmaceuticals and materials science.
One primary use is in drug discovery, simulating molecular interactions. Quantum computers accelerate simulations of complex molecules, enabling faster identification of potential drug candidates.
Another application is in materials science. Quantum computers model new materials with unique properties. This impacts industries from aerospace to electronics.
Cryptography is also poised for transformation. Quantum computing can break and enhance encryption. Quantum cryptography offers unbreakable encryption techniques. The transformative power of quantum computing is vast and far-reaching. Section 8: Technical challenges. Developing stable quantum computers presents numerous technical challenges. One of the biggest hurdles is quantum decoherence. Decoherence occurs when qubit states are disturbed, leading to errors in computation. Maintaining qubit stability requires precise conditions. Environmental factors like temperature and electromagnetic interference can cause decoherence.
Researchers are exploring ways to isolate qubits and extend coherence times. Advanced error correction techniques are also under development. Scalability is another challenge facing quantum computing. Building systems with a large number of qubits is complex. Each additional qubit increases the difficulty of maintaining coherence.
Innovations in architecture and materials are essential for scalable solutions. Quantum algorithms require efficient implementation. Designing algorithms that leverage quantum advantages is an ongoing research area. The development of quantum software is crucial for practical applications. Efforts are underway to create frameworks that simplify quantum programming.
Despite these challenges, progress continues. Researchers and companies are making strides in overcoming technical barriers. Collaboration across disciplines is vital for breakthroughs. As these challenges are addressed, the realization of practical quantum computers comes closer.
Section 9: Ethical and security concerns. The advent of quantum computing raises ethical and security concerns. One major issue is the potential to break current cryptographic systems. Quantum algorithms could render traditional encryption methods obsolete, threatening data security.
This vulnerability necessitates the development of quantum-safe cryptography. Researchers are working on new encryption techniques that resist quantum attacks. The transition to quantum-resistant systems is crucial for future data protection.
Technological inequality is another concern. Quantum computing could widen the gap between advanced and developing nations. Access to quantum resources may be limited, exacerbating existing disparities. Ensuring equitable access will be a key challenge for policymakers.
Ethical considerations also include the use of quantum technology. Its applications in surveillance and privacy must be carefully managed. As quantum computing evolves, regulations will be needed to govern its use responsibly. Balancing innovation with ethical considerations is essential.
Engaging diverse stakeholders in discussions about quantum technology is important. Addressing these concerns early can guide the responsible development of quantum computing. The goal is to harness its potential while minimizing risks. Section 10. Future opportunities. The future of quantum computing is filled with opportunities. Its transformative potential spans across science, industry, and society. As technical barriers are overcome, quantum computing will unlock new possibilities. One promising area is artificial intelligence. Quantum computing can enhance machine learning algorithms. This could lead to breakthroughs in pattern recognition and decision-making. The combination of AI and quantum computing promises unprecedented advancements. In healthcare, quantum computing could revolutionize personalized medicine. It can analyze vast amounts of genetic data to tailor treatments. This precision approach can improve outcomes and reduce healthcare costs.
Environmental applications are also significant. Quantum simulations can improve climate models, aiding in understanding climate change. This can inform better policy decisions and strategies for sustainability. Quantum computing can contribute to addressing global challenges.
The broader implications of quantum computing are profound. It has the potential to reshape economies and societies. Collaboration and innovation will drive its development. As we embrace this technology, we must consider its impact on future generations.